question we centered on what we did from chapter 5 to chapter 10. I think I send you, you can see the announcement section for that. Like I said, I'm so glad about, I'm so happy about the performance and what will justify the salary I'm getting, this the wage, is when when I've done my best and I realize that my students are doing well. I'm so happy about that. Okay, I want to welcome you to another exciting statistical topic. We started this chapter 9 last week on 1 and 2 sample estimation problem. I'm going to call that part 3. Okay, and of course, in the outline, I'm actually going to walk you through how do we compare two means that are matched pairs. Of course, you know, that was left undone in the lecture material for last week. Okay, I'm actually going to go over that with you. Then we're also going to talk about the confidence interval for difference of proportions. Then we're also going to talk about, you know, if, you know, looking at the hypothesis testing too. Okay, now let's start with this. Paired observations. What do I mean by that? Even though I got two groups, but they depend, you know, before now, we've worked on comparing means in two populations. Do you know there are 3 things that we've done before that has to do with comparing means in two populations? When I say two populations, what do I mean? Two independent populations, two independent groups. Do you know, number one scenario is, do we have population variances for the two populations? Or do we have population standard deviation? If we have the population variances or population standard deviation, of course, we're going to use a z-score. I think I'm going to write something now. We're going to use a z-score that has to do with this guy. Now, do you know when we use this guy? When we want to construct a confidence interval of difference of means between two independent groups where the population variances are given. Okay, that's why you say sigma 1 square. This is one case scenario. Another case scenario is when the population variances are not given, then you know what is going to happen. In the case they are not given, okay, this guy will be replaced by T. Okay, and the sigma 1 squared will be replaced by this guy, and sigma 2 squared will be replaced by that guy. Okay, so when the population variances are not given and are assumed not, you know, they are not given and are assumed not equal. If they are not given and they are assumed not equal, okay, then I'm actually going to use, the formula is going to change. And not only that, the degree of freedom, okay, is basically going to be a complicated expression, if you can check your notes. Then another situation, when you're constructing a confidence interval, when the population variances are not given, but they are assumed to be equal, then you need to compute a pool variance. Okay, you're going to compute a pool variance. I remember in the pool variance formula, you're actually gonna have this guy. You're gonna have XP, 1 over n1 plus 1 over n2. Okay, this is the third scenario. Okay, so here I'm actually going to have x bar 1 minus x bar 2 plus t xp 1 over n1 1 over n2, and your xp is going to be square root of n1 minus 1 s1 squared n2 minus 1 s2 squared divided by n1 plus n2 minus 2. Okay, this is the third case scenario. Okay, the third case scenario when the population variances are not given, but they are assumed to be equal. Okay, assumed, okay, to be equal. Okay, unknown and assumed to be equal. Okay, we're going to use that. And the degree of freedom is basically this. Okay, the degree of freedom is basically that. Okay, but what if in a situation where I'm no longer looking at the difference of means in two independent groups? This time around, the group are dependent. What do I mean by group being dependent? Because we're using the same subject at different occasion. It's just like we collect data from you. Maybe, oh, okay, this is a good example. Maybe I compare your mid-time 1 score with mid-time 2 score. The same person, okay? Is the two group independent? No, dependent, because I'm using the same participant, except that the participant were visited at different occasion. Let me ask this question. Is there anybody who is struggling in this class with the way I speak? Is there anybody who doesn't understand my English? Because I used to ask anywhere I go. I was not born in the United States, but I basically want to try and communicate, because communication is the key. Is there anybody who doesn't really understand the way I talk, like my accent, or is struggling with that? Is there anyone? Do not hide your feelings. Okay, so what I'm trying to say now, we're going to call that kind of observation period. Why period? Because we're collecting data from the same person at different occasion. If I now want to construct a confidence interval for that, do you know I'm not going to call that difference of means? You know what I'm going to call that? Mean of the difference. Difference of means is different from the mean of the difference. The one we've been doing, the three-case scenario, the three-case scenario that I just mentioned now, we call them difference of means. Okay, we only talk about difference of means, okay, when two independent groups are involved. When you are talking about two independent, look at the word independent. I can talk about difference of means. But situation where the groups are dependent, where you are getting the information from the same person at different occasion, we don't call it difference of means. We call it what? Mean of the difference. The English is not the same. Mean of the difference. It means if I have occasion 1, occasion 2, okay, occasion 1, occasion 2, I'm going to get the difference, x2 minus x1. Now the difference become a random variable, then I need the average of the difference. And that's why we call it mean of the difference. We use mean of the difference when the groups are dependent, when you are talking about dependent group. Okay, now the question now, if I want to construct the confidence interval now on the mean of the difference, this is the formula that I'm trying to show you now. Where D bar, look at the D bar. The D bar is the mean of the difference in the sample. Does that make sense to everyone now? There's a difference between having an independent groups with dependent groups. Does that make sense now? Okay. Now, take a look at this example. A study published in Chemosphere reported the level of the dioxin TCDD of 20 Massachusetts of Vietnam veterans who were possibly exposed to Agent Orange. The TCDD levels in the plasma and the fat tissue are listed in that table. I'll find a 95% confidence interval for that. Now, you know, when you see the veteran, how many veteran? 20. This 20 veteran, they were exposed to two different experimental conditions. If you take a look at veteran number 1, okay, we actually get the TCDD levels in plasma. We measured that for that veteran number 1, that was 2.5. On the same veteran number 1, we also measure TCDD level in the fat tissue, which means I'm getting two different measurements from the same subject, and that actually make that to be a repeated trial. And because of that, I'm actually going to use a paired. That's what I'm. That's a paired one. Okay. Now, all what you're going to do, take a look at what is on the board. What is the difference between that 2.5 minus 4.9? You can see the difference now. The difference is actually DI, but you know what we want to get? We basically want to get a confidence interval for the true, mean of the difference. Okay, in doing that, the very first thing we're going to do, there are two statistical measures that we need to first do. Take a look at that. From the DI, we actually need the mean. We need a standard deviation. Does that make sense? We need the mean of the DI, mean of then the standard deviation of the DI. And the standard deviation of the DI, look at the formula, I got 2.9773. Okay. And the mean of the DI was negative 0. For those of you who doesn't know how to obtain that. For those of you who doesn't know how to obtain that, okay, D bar high is summation of DI. I start from 1 to n divided by n. Okay, so that is what we actually, how we added all the D high. Okay, for how many observations? I think for 20, we divided by 20, we got the mean. We're also going to get the standard deviation. Even though we got some values that are negative, standard deviation can never be negative. But you know what the mean can be negative. I want you to take note of that. Standard deviation can never be negative, cannot also be 0. So take a look at that. Now, all what you're just going to do, plug in, we're using this particular formula here. Take a look at that. Okay. SD is the standard deviation. When you see S subscript D, means standard deviation of the difference. Does that make sense now, right? When you see the mu D, when you see this guy, okay, this guy is the true mean of the difference. Okay, this guy here, okay, sample mean of the difference. There's a difference between this guy and this guy. Between the sample mean of the difference and between the true mean of the difference. But when you are calculating, when you are constructing confidence interval, okay, we are actually assuming population. We're not assuming sample, even though we're using sample data, right? If you take a look at what is in the middle, I'm actually writing mu D. Even though I'm focusing on 20 veterans, that very mu D, okay, is giving the mean difference of all veterans, not only 20. And that is why, please take notes. If you write SD in the middle, S bar D, if you write this guy in the middle of that formula, you are technically wrong. Does that make sense now? It's going to be population value for whatever you do, not only for this. Okay, now at the degree of freedom, we say -1. I got 20 veterans. The degree of freedom is going to be 19. Of course, when I go into the table, right? Okay, under the degree of freedom 19, okay, with the level of significance, if I'm giving 95% confidence, okay, if I'm giving 95% confidence, the level of significance will be 5%, right? 0.05. Okay. Now you're going to do alpha over 2 because when you are constructing confidence interval, you are considering two-sided, error to the left, error to the right. Then you divide alpha by 2. So 0.05 divided by 2, that would be 0.025. So which means I'm actually going to check the T table, okay, under the degree of freedom 19, and 0.025 level of significance, that will give me 2.093. That's what I'm going to plug in there. Now look at what I got at the end of the day. How do we interpret when you are interpreting confidence interval? You shouldn't base that on sample. You're going to base that on the population. Look at what I said, from which you can conclude there's no significant difference between the mean TCD level in the plasma and the TTC level. Did I say for the sample? Now, what am I doing here? Do you know the idea of the confidence interval can be used in hypothesis testing? I'm going to say that again. The idea of confidence interval can be used in hypothesis testing. How? Look at the range of values that we got. We got from negative to positive, right? When you have, if your lower endpoint is negative and your upper endpoint is positive, what can you see in the interval? There can be 0 in the interval, right? That means 0 lies in the interval of what? Negative and positive. This is what I'm saying. Take a look at this guy now. What is this? Negative? Positive? Anytime you are from negative to positive, zero can be found in the interval. And if the 0 is found in the interval, that indicates insignificant. I'm going to say that again. Insignificant. What do I mean by insignificant? It means the difference between what you measured in the first occasion and the second occasion, even though difference exists, that difference is not significant. Does that make sense to you? But what if you get from negative to positive, or you get from positive to positive, from negative to negative, from positive to positive, there's no 0 in the interval. Does that make sense? If there is no 0 in the interval, you know what that implies? Significance. Does that make sense now? That implies significant difference. We appreciate the fact that in statistics, difference exists in the world we find ourselves. But something that we can call difference is when the difference is significant. Does that make sense now? And that was what we mean. Now, I want to go into proportion. We've been talking about mean, right? We've been comparing means, right? What if in a situation where we want to focus on the proportion and we don't want to just get a point estimate? A point estimate could be wrong or right. A point estimate is when you get a single value. A single value could be wrong or right. And we now want to get a value that will be in the interval. Why? Why do you think I want to get a value in the interval? Because all the values in the interval cannot be wrong, but a single value could be wrong. Now, talking about proportion now, maybe I'm interested in how many senators approve of, Biden proposal on student loan forgiveness, because I want to believe it's not all senators in the United States that support that. That's a proportion. If I'm not interested in just a point estimate, but I want the result to be reasonable. I want it in an interval so that I can boastfully say, okay, the proportion of those who support, or the senators who support Biden agenda on student loan forgiveness probably lies between this and that. It makes more sense when you present your results in an interval. Okay, now what formula are we going to use? That is a formula. Although we have the method 1, we have method 2. Method 2 is complicated. Method 1 and method 2, they basically going to, the result, the difference between the result they're going to get is marginal. And that's why we're going to go with method 1. But there's something I want you to take note. In the formula, when we're dealing with the proportion, there's always going to be z-score, not t-score. No condition under which you're going to have a t as part of the proportion formula. Does that make sense to everyone? Whether you are dealing with the proportion for one population or for two populations, it's always going to be a z-score. Now you can see the formula now. Now let's go into the example. In a random sample of 500 families owning television sets in the city, Hamilton, Canada, it was found that 340 subscribed to HBO. That's a proportion. Because it is not everybody. Categories always exist in this world. We cannot reason the same way. We always going to, our ideas or our, behavior or whatever, there's always going to be variation. Therefore, proportion exists. Take a look at this now. Out of 500 families who own television, it is not all of them that subscribe to HBO. Okay, maybe HBO is a TV station in Canada. Does that make sense now? Now find a 90% confidence interval for the actual proportion of family with television sets in this city that subscribe to HBO. Do you know if I want to get a point estimate, what am I just going to do? That's going to be the ratio of the number of those who possess that characteristics of interest divided by the sample space, by the sample size. In this case, it's going to be 340 divided by 500 is 0.68 here is a point estimate. Point estimate. It's a point estimate. And you know what? This is what we mean. Point estimate. And I said is a single value. Okay, a single value, okay, that we got in an estimation process. But you know what? That single value could be wrong or right. The probability that is going to be wrong and right is the same. You can see why we don't want to. It's too dicey. And that's why we need a confidence interval. Okay, now plugging that in now, we got a P. Now, do you know this guy is gonna make sense now? You know what we're gonna say? Oh, the proportion of those who host TV in this city that actually subscribe to HBO, that percentage is going to be between 63.91 and 72.09%. That makes more sense compared to when I just say, okay, 68%. Now, let me tell you this. The confidence interval tells us how reliable is our point estimate. It tells us how the results of the survey reflects the overall view in the population. And that is why we've incorporated the margin of error. We subtract from the point, we added to the point. That was why we got two endpoints. Why we got the lower endpoint and the upper endpoint. Does that make sense now? Okay. Now we want to go to two different groups. We've been comparing groups. When we are comparing groups, what are we comparing? We could be comparing means. We could be comparing proportions. I've walked you through when you are comparing means in two different groups. If the group are independent, there are three case scenarios. that I've walked you through in this class. Okay. And if the two groups are dependent, I think I just walk you through the paired one. Okay. Now take a look at this example, comparing the average GRE score before and after taking a pre-course. Okay. Before and after. That's going to be a dependent group. That's this pair one for means. Take a look at the second one. Compare the proportion of Minnesotans who own guns to the proportion of Wisconsinites who own guns. That's the proportions. That means you are testing proportions in two different populations, Minnesota and Wisconsin. They are independent group. Okay, what are we going to do? Okay, what is the formula? Of course, the goal is to compare proportions in two independent samples. And this is what we're going to do. You know what we're looking for? The true value for if the proportion of everyone who owns guns in Minnesota, maybe I'm going to call that P1, the one without cap. The P2, the one without cap is the proportion that owns guns in Wisconsin. But do I have resources to study everybody in Minnesota, everybody in Wisconsin? We don't do that. We're actually going to take a sample, right? And 1 would be the sample that I choose from Minnesota, and 2 is the sample that I choose from Wisconsin. X1 is the number of, residents of Minnesota that owns guns. And X2 will be the number of residents in Wisconsin that own guns. Then what is the pickup 1, pickup 2? Oh my God, the pickup 1 would be the sample proportion of those who own guns in Minnesota, and pickup 2 will be the sample proportion of those who own guns in Wisconsin. Now, what am I looking for? I'm actually looking for P1 minus P2, the difference, the one without a cap. I'm looking for the difference for the general, for everybody in the state, for those who own guns in Minnesota and those who own guns in Wisconsin. But you know what? There's no way I will be able to get that exactly. Then I will need to estimate. That was why you see a cap, right? Pickup 1 minus pickup 2. When I do the difference of pickup 1 and pickup 2, you know what I'm going to get? I'm going to get a single result, which could be wrong or right. Then I'm actually going to call point estimate. Then what do I need? Then I need an interval. And before I can have an interval, of course, I show you the other time, the mean of that guy is actually P1 minus P2. The standard deviation is this guy. Now, the pickup 1 minus pickup 2 follow normal distribution with the mean of that and the standard deviation of that. But let me tell you this. I can ask you in exam before we can construct a confidence interval for difference of proportion. Which assumption that is required? The product of N and P must be greater or equal to 10. I'm going to say that again. Before we can actually, construct a confidence interval for difference of proportion, we require that the sample size taken from the population 1 multiply by the P1 has to be greater or equal to 10. This is what I mean. You know the assumption now. The assumption now is that N1P1 must be greater or equal to 10, N2P2 must be greater or equal to 10. Not only that, N1 into 1 minus P1 must be greater or equal to 10, N2 into 1 minus P2 must be greater or equal to 10. This is a special requirement. That's a special requirement. Okay. Now, that was what I call at least 10. Okay, now let me show you the formula now. Do you see the formula now? That is a formula. And you're always going to say is this a z-score, not a t. Whether you are dealing with a confidence interval for proportion for one group or for two groups, it's always going to be a z. Okay, now look at the assumption now. Number 1 assumption, the sample that you're going to be choosing from the two populations have to be independent. And what can you do to generate the, to actualize that independent? Of course, when you're taking sample randomly, when you give equal chance to everybody, and of course, at least 10 successes and 10 failures in both. That is what I demonstrated here. This is successes. This is successes. This is failures. Okay? Does that make sense now? So take note of that. Now let's go to an example now. Okay? And let me tell you this. When an interval includes 0, not significant. When an interval does not include 0, significant. Now, let's take a look at this example. The NCAA requires college to report the graduation rate of the athletes. Anytime you hear something about rates, that's a proportion. The idea of proportion can be used. In a sample of former male and female student athletes, 43 of the 53 females survey had graduated, where 58 of 102 male are graduated. Calculate and interpret a 99% confidence interval for the difference in true proportion of female athletes who graduated and the male athletes who actually graduate. Let me tell you this. We have male and female that play sports. We now want to compare their graduation rates. We can construct a confidence interval of the difference of the graduation rate between male and female. Of course, the male and females are independent groups. Now, you need to first investigate whether the assumption hold. Okay? Now, of course, the number of successes that you see, 43 and 58, they are both greater than 10. Is you can actually use this approach. Then what is the pickup for male? What is the pickup for female? That's what we found. Then this is a 99% confidence interval. You just plug all that in. For 99%, okay, for 99%, the alpha is going to be 0.01. Divide 0.01 by 2. That will be 0.005. You're actually going to go to Z table. You can see what you have now. You see that? You get this result. How am I going to interpret this? I said we are 99% confident that the true proportion of female student athletes that graduate is between that and that, higher than the true proportion of male student athletes. Why do I say higher? Higher in the sense that the two values that I got in the interval are both positive. Does that make sense? Can I get 0 in this interval? Can we get 0 in the interval? No. When there is no 0 in the interval, you know what that means? That's a significant result, which means the graduation rate of female, okay, and it's actually more than that of the male. Any question? We're done. Any question with this? We're done on this. Any question? Okay. I want to go into, we just talked about the confidence interval now. We now want to go into the hypothesis testing. This is part of chapter 10, hypothesis testing. But because I'm actually talking about confidence interval for difference of proportion, and I wanted to see the difference between the two when I'm talking about hypothesis testing for that. Now, I want to introduce you to what we call hypothesis testing. What do we mean by that? Hypothesis is an intelligent guess about the value of a parameter. I'm going to say that again. Hypothesis is an intelligent guess. Hypothesis, okay, is an assertion or intelligent guess about the value of a parameter. I told you the other time, parameter is whatever we want to know that we don't know. Okay? Anything that we want to know that we don't know, that's a parameter. But you know what? Our mind can never be empty. There's always going to be a value for that in our mind. But we're not too sure whether that value is right or wrong. And that's why we actually want to test that value. It's just like somebody accused me of wrongdoing. Okay. The fact that the person accused me of wrongdoing does not mean that the person is right. You know what I'm going to do? Take me to court or justify my wrongdoing. Okay. So if there's an hypothesis, okay, if there's a claim, an investigation will always follow a claim. Does that make sense? Now, investigation following a claim means I'm testing, I'm conducting an hypothesis, testing about the value that I have in mind or about a claim. We're actually going to have what we call the non-hypothesis, which we call HO. We're going to have the alternative. The non-hypothesis here, if I'm talking about two groups, we'll be talking about equality. Oh, this proportion here is the same as this. But you know what the alternative can be? Alternative can be any of these three: less than, greater than, not equal. Let me use this as an example. The other time, we constructed a confidence interval between the proportions of those who own gun in Minnesota and those who own gun in Wisconsin. Now, when you take a look at the first hypothesis, it's under the HO, it's trying to say there is no significant difference between the proportion of those who hold gun in Minnesota and those who hold gun in Wisconsin. But do you know what the alternative is saying? The alternative is saying the proportion of those who hold gun in Minnesota is less than that of Wisconsin. Take a look at the second set of hypotheses. It's saying it is greater, right? If you take a look at the third one, it says it is not equal. Now, in the question in the exam, you need to be able to identify whether your alternative is going to be less than or greater than or not equal. If it is less than or greater than, that's what we call one-tail test. One tail. That's what we call one-tail. One-tail test. If it is not equal, that's what we call two-tail. Two-tail tails. Now, what do we mean by one-tail? That is directional test. This is directional. This is non-directional. Okay. In the non-directional, you have less than. Oh, sorry. In the directional, you have less than, greater than. Okay. But in the non-directional, you have not equal. That's non-directional. Okay. Now, the Z statistic that we're going to use is this guy here. What is the meaning of that zero? That zero is when the non-hypothesis is true. When P1 equal to P2, it means P1 minus P2 equal to 0. And, this is a formula that we actually use. Okay, of course, we told you the P1 curve minus P2 curve follow that distribution. And let me also tell you this. When we calculate our Z-score, we need to figure out the p-value. Because if we want to take a decision, we're going to compare our p-value with the level of significance. When the p-value is less than the level of significance, we are rejecting HO. When the p-value is greater than the level of significance, we're going to fail to reject HO. But let me tell you this. If I want to figure out my p-value, that depends on the nature of the alternative. I'm going to say that again. If you take a look at this, if you look at the alternative HA here, less than, greater than, not equal. If I want to figure out the p-value of a test, then I need to be able to understand in this example, what is the nature of the alternative? Take a look at it. For hypothesis 1, where I'm talking about less than, where the alternative is less than, okay, I need to calculate the probability of Z less than. In hypothesis 2, where it is greater than, the p-value will be the probability of the z-statistic greater than. In hypothesis 3, where it is not equal to, then it's going to be 2 multiplied by the probability of z greater than greater than the absolute value of z. So what does that mean? If you want to get your p-value right, you need to get the nature of the alternative right. Does that make sense? Okay, and the moment I get my p-value in the decision rule, what I'm just going to do, or I have 5 minutes, what I'm just going to do is to compare the p-value with the level of significance. The level of significance is called the level of statistical error. We also call it the maximum probability of committing type 1 error. I'm still going to tell you 2 types of error in research. You know, we have type 1 error, we have type 2 error. Still going to talk about that. Okay, now I'm going to walk you through this example now. Take a look at this. Survey USA polled 500 Americans and asked if marijuana should be legalized for medicinal purposes. The result of this survey are summarized in the following contingency table, where they look at the age. The age is categorical, less than 50 years and 50 years or more. Okay, and the other variable is the response. Legalize it or don't legalize it. 202, okay, that are less than 50 years of age said they should legalize that. And 108 said no, don't legalize it. And the total number of people that consider legalizing is 320. The total number of respondents that go against that is 180. But you know what we want to find? Take a look at the A. So use this information to test at the 0.05 level of significance whether younger people are more likely than older people to think marijuana should be legalized. You know what you're going to focus on? You are comparing age, and you are also focusing on the legalized age and the legalized, okay, which means what is the proportion that supports legalized at age less than 50? It is 202 divided by 310. 310 is the totality of people that are less than 50. You also do the same for the other one. You got these 2 proportions. We can test an hypothesis about that. We not only test an hypothesis, we can also construct the confidence interval on that. The result of the confidence interval will agree with that of the hypothesis testing. Okay, take a look at that now. Okay, now when we do that, you get your, how do I know my alternative is greater than? I know from the question. Look at that. Look at that. More likely, more means greater than. In another question, it may be less. Okay, that was how I know. When you are specifying your hypothesis, if you have a wrong specification, it will affect other things you're going to do. Then from there, we get a z-score. Then we get a p-value. Look at the p-value now. Why do I say probability of z greater than? Because the alternative is greater than. If the alternative has been less than, then I'm going to do the same. Finally, I compare my results. The p-value that I got is 0.2451, and that is greater than the 0.05. And I'm basically going to fail to reject. Okay, that's what we're going to start from on Wednesday. Any question on what we've done today? Very interesting, right? Any question? Any question? Now I give you your booklets, exam booklets. If you have any question, maybe I made a mistake, please let me know. Make sure you stay safe and have a lovely day. Bye for now, everyone.